If I can't picture it, I can't understand it. Albert Einstein. Welcome, students. Today in Dynamics of a System of Particles, we discuss center of mass reference frame. This idea we divide two parts, part A and part B. In part A, we discuss Newton's laws and momentum method. In part B, we discuss methods of work energy. As we know that all the methods of mechanics can be classified into three categories. One is based on Newton's law. Second one is based on methods of work energy. And third one is based on method of impulse and momentum. So today we'll discuss about Newton's laws and momentum method. Methods of work energy will postpone for the next lecture. Now before we proceed, I want to draw your attention on the idea from where concept of mass center was developed. That was developed from the equation that if you add moment of all the particles of a system, it will represent total amount of translation motion of a system. And this we can write mathematically as mass of the entire system into velocity vector of the mass center. In this way, velocity vector of the mass center will represent motion of mass center. In so many situations, what we find, motion of mass center is very simple. In some case, it will be at rest. In some case, its motion will be more simple or simplest from all the particles of the system. Let us see here two particular example. This example we have discussed in the introductory screen on the center of mass lecture. A rod has been thrown and while in the air it rotates. How can you throw a rod like that? Hold it from one end and throw. So it will move in the air and rotate also. So if we concentrate on any of the particles other than the center particle, say this particle, so this particle will move like that. So motion of this particle is very complex. Similarly, all the particles other than the center particle, their motions are very difficult, very complex. But central particle, you can see it is moving on a parabolic path as if this rod were a particle of mass m concentrated on the mass center. So in this case, we can see the motion of mass center is parabolic, and this motion we can predict with the help of Newton's laws. Similarly, here you can see second situation. A plank is placed on a horizontal floor and man is standing here. And if man walks on the plank, it will push the plank backward, and if there is no friction between the plank and the floor, the plank will move backward. Now you can see in this case, there is no horizontal actional force on the man-plank system. Now, while developing Newton's law for a system of particles, at present, we see that the net actional force will be equal to total mass of system into acceleration of mass center. So in this case, what you can see? In horizontal direction, there is no acceleration of mass center. So before man starts walking, the mass center was stationary. So during the entire motion of the man, the mass center will be stationary. So in this case, mass center will represent a very simple reference frame to analyze this problem. Now, before dealing with several problems, we'll discuss about what is center of mass frame and some of its fundamental properties so that we can realize how mass center will represent simpler solution. There is one more thing about reference frame. We have experienced that while analyzing a particular problem, some reference frame may represent very simple solution. How we select a particular reference frame which will be most suitable for a particular problem? This is done with the two guidelines. First one, if in the problem, few quantities are given with respect to some reference frame or asked with respect to some reference frame, then use that reference frame with respect to which quantities are given or asked. That idea will be simplest one. Otherwise, if it is not so, quantities are given in ground frame and asked in ground frame, and we start analyzing problem in the ground frame. In the solution process, sometimes there may be some intermediate quantities which may become too cumbersome to calculate or impossible to calculate. In such situation, if we can find a particular reference frame in which these problem creating quantities either become zero or will become simpler to calculate, use of that frame will be preferable. In this way, reference frame of center mass presents several times very simple solution. So let us come to discuss what is center mass frame and its fundamental properties. Center mass reference frame. Center mass reference frame of a system is a non-rotating reference frame, origin of which is the mass center of the system. It moves together with the mass center. Actually, here the term non-rotating is very important. Actually, it is convention. If it is not mentioned that a frame is rotating, we always take non-rotating reference frame. So, in problems to come, I will never say that non-rotating. It is convention that if it is not mentioned the frame is rotating, we have to take it non-rotating. So, what is center mass frame? Center mass frame is a non-rotating reference frame, origin of which is attached with the mass center. So, center mass frame will move together with the mass center. This reference frame presents a very simple interpretation and solution to several physical phenomena. Let us first discuss some of its fundamental properties so that we will be able to visualize or we will be able to understand how this reference frame will simplify solutions. The first property is sum of mass moments in the center mass frame is a null vector. What is mass moment? Mass moment of a particle is product of mass of the particle and its position vector. And mass moment in center mass frame will be what? Product of mass of the particle and position vector of the particle with respect to mass center. So particle 1, what it will be? M1 into R1 with respect to C. For particle 2, what it will be? M2 into R2 with respect to C. So let us write sum of all such terms. So here, what is the mass moment? Mass moment of a particle is product of mass of the particle and its position vector. Now, in center mass frame, what it will be? M1 R1 vector with respect to C plus M2 R2 vector with respect to C and so on. For ith particle, it is Mi Ri vector with respect to C and so on. For nth particle, it will be plus Mn into Rn vector with respect to C. This will be a null vector. This equation we can write in simple form as summation Mi Ri with respect to C is equal to null vector. Now, how can we understand why it is so? Actually, R1 with respect to C is R1 vector minus Rc vector. R2 with respect to C is R2 vector minus Rc vector. It is Ri vector minus Rc vector. It is Rn vector minus Rc vector. Now, substitute all these relations. So, what we get? M1 R1 vector minus M1 Rc vector plus M2 R2 vector minus M2 Rc vector, Mi Ri vector minus Mi Rc vector, and similarly Mn Rn vector minus Mn Rc vector. Now separate the terms, Rc terms at once. So, and what is M1 R1 vector plus M2 R2 vector plus and so on plus Mn Rn vector minus Rc vector, take common, what you get? M1 plus M2 plus Mn into Rc. And you can see this equation by center mass definition is 0. Or sorry, null vector. So in this way we can write that total mass moment of a system in center mass frame will be a null vector. Now what is second property? Total linear momentum of a system in the center mass frame is a null vector. That is very simple idea. If you use momentum method in center mass frame, what we get? Always total momentum will be 0. So we can write here M1 V1 vector with respect to C plus M2 V2 vector with respect to C and so on. Similarly for ith particle, what it will be? Mi Vi vector with respect to C. And for nth particle, what it will be? Sum Mn Vn vector with respect to C is equal to null vector. This equation in simple form can be written as summation Mi Vi vector with respect to C is equal to a null vector. As we have proved it to be null vector, in the similar way, we can prove it to be null vector. So what we can see? Total momentum of a system in center mass frame will be a null vector. That is very great idea. Now, what is the third property? Total effective force in the center mass frame is a null vector. So what is effective force? Effective force is product of mass into acceleration. So what is M1 A1 vector with respect to C plus M2 A2 vector with respect to C and so on. So what we can write here? M1 A1 vector with respect to C plus M2 A2 vector with respect to C. For ith particle, it will be Mi ai vector with respect to c, and for nth particle what it will be, plus mn, an vector with respect to c is a null vector. And this equation can be written in simpler form as summation mi ai vector with respect to c is a null vector. Of course, these two equations we can obtain by differentiating this first equation. So again, total effective force in a center mass frame is a null vector. What is the next property? Total work done by pseudo forces in a center mass frame is zero. That is again very important property. So when we use work energy method in center mass frame, in addition to physical forces, if center mass is accelerated, we have to account work done by pseudo forces also, and fortunately total work done by pseudo forces in center mass frame is becoming zero. So it is a great simplicity. So how we can write pseudo force? Pseudo force is mass into acceleration of reference frame in reverse direction. So if center mass has acceleration AC, so on a particle of mass m, what will be pseudo force? Minus m into AC. So m1, what will be pseudo force? m1 into minus AC. Similarly, what will be pseudo force on m2? m2 into minus AC, and sum of all these terms pseudo force, and their work done will be zero. How we calculate work done? To calculate work done, let us see a very infinitely small interval in which a particle r1 has displacement dr1 with respect to c, and similarly r2 has dr2 with respect to c. So to calculate work done of pseudo force on any particle, what we do? We do dot product of pseudo force on that particle into infinitely displacement of that particle. So for m1, what it will be? Minus m1 AC dot r1 with respect to c, and we try to sum all such terms. So let us see, minus m1 AC vector, that is pseudo force, into dr1 with respect to c, that is infinitely small displacement. For ith particle, minus MIAC into dRi with respect to c, infinitely small displacement. And similarly, we can write for the nth particle, what will be? Minus MNAC dot DRN with respect to c. How it will be in null vector? From all these terms, minus AC we can take common. So if you take minus AC, what is remaining in the bracket? You can see the and D of this. And again, you can take differential of the entire equation. So what we can have? Minus M1C dot D in bracket, this one. So this is 0. So in this way, what we can say? Total work done by pseudo forces will be 0. That will deduce again while discussing methods of work energy. So what we can see here, this equation we can write in simpler form, that is minus MIAC dot DRI with respect to C is 0, means total work done by all the pseudo forces in the center mass frame is 0. All the above properties or ideas are applicable for continuous mass distributions, employing definite integral over the entire mass distribution. Actually, this idea we have written for discrete masses, they can equally applicable for continuous mass distribution. If there is continuous mass distribution, in place of summation sign, what we use? Integration sign. Now let us come on a few simple examples in which we try to identify velocity at mass center and velocity and acceleration with respect to mass center, these things. Say example 1. What is that? A jeep of mass 2400 kg moving on a state level road at 80 km per hour due east is being followed by a car of mass 1600 kg moving at 60 km per hour. So both jeep and car are moving in the same direction in east. Jeep has velocity 80 km per hour. The car has velocity 60 km per hour. What is asked? How fast is the center of mass of the two cars here? Jeep is also a car, is moving. So how we calculate velocity of mass center? That is very simple. Vc is equal to m1v1 plus m2v2 upon m1 plus m2. Here 1 stands for jeep and 2 stands for car. So how we can write velocity of the mass center of jeep car system, that is Vc is equal to mass of jeep into velocity vector of jeep plus mass of car into velocity vector of car upon mass of jeep plus mass of car. Now let us substitute values. So Vc is equal to 2400 into 80 plus 1600 into 60 upon 2400 plus 1600. How? Actually, we should start always from vector equation. Now, depending on situation, we substitute values. So we started from vector equation. Now we know the problem is one dimension. The motion is always east to west. So we are assuming east direction to be positive and west to be negative. Both these velocity in east, so we have taken them positive. So by solving this, what we get? Vc is equal to 72 km per hour due east. So center mass moving with the 72 km per hour in the east direction. Now in part B, what we have to calculate? Find velocities of both the vehicles in the center of mass frame. Now again, we start with vector equation. So how will that velocity of the jeep in center of mass frame, what it will be? Velocity of jeep with respect to c is the velocity vector of jeep minus velocity vector of the car. And now while substituting value, we can see, yes, it is a one-dimensional motion. And we assume east to be positive and west to be negative. So velocity of jeep is 80 due east, so it will be positive. Velocity of center mass 72 due east, so it will be positive. So velocity of jeep with respect to car is 80 minus 72, that is how much? Velocity of jeep with respect to car is 8 km per hour. It is coming positive, so it will be towards east. I will recommend you, while using these relations, start with vector form. Especially while using relative motion equation, start always with vector form. Actually, whenever a one-dimensional situation comes in relative motion, at that time, we think that yes, it is very simple. And in that excitement, we commit several times mistakes of sign. So what I suggest, use the vector equation and then substitute values according to sign. Similarly, in the same way, we calculate velocity of the car with respect to mass center. So velocity of the car in the center of mass frame, what it will be? Velocity of car with respect to mass vector is equal to velocity of car vector minus velocity of c, mass center, as a vector. Now we substitute values. We assume east to be positive. So velocity of car with respect to c is equal to 60 minus 72. Now what is coming? It is coming minus 12. Minus 12 means it is opposite to east. So we can write here 12 due west. So velocity of car with respect to c will be 12 km per hour due west. So in this way, we can get exact direction. So what is part C? Find total momentum system of both the vehicles in the center mass frame. We know as a priori that total momentum of system in center mass frame is zero. Sorry, null vector. If I say zero, it means we are taking its magnitude zero. So magnitude of null vector is also zero. So here, let us verify the idea. So what we do, we multiply this mass with this velocity and this mass with this velocity. So here it will minus sign and we add. Let us see. So summation mi, vi with respect to c. So that is mg into velocity vector of g with respect to center mass plus mass of car into velocity vector of car with respect to center mass. Now we substitute values in scalar notation. We take east to be positive and west to be negative. So here this velocity will be positive sign and this velocity will be with a negative sign. So what you get? Denoting the east direction by positive sign, we get mi vi with respect to c, that is what? 2400 into 8 plus 1600 into minus 12, and by solving this you will get 0. So that is verification of the idea. So this simple calculation we have done in a two-dimensional situation, that is one-dimensional situation. Let us take them in a two-dimensional situation so that we can become familiar with the using these ideas in I cap J cap notations. Example 2. A 2 kg particle has a velocity of v1 vector is equal to 2 I cap plus 3 j cap meter per second, and a 3 kg particle has a velocity v2 vector is 1 I cap plus 6 j cap meter per second. Part A. Find velocity of the center of mass of the two particle system. So how we can find velocity? That is again m1 v1 vector plus m2 v2 vector upon m1 plus m2. So we'll use the idea here. Velocity of the mass center is vc vector is m1 v1 vector plus m2 v2 vector upon m1 plus m2. Now we substitute the values. For m1 we substitute 2, for v1 we substitute this, for m2 we substitute 3 kg, and for v2 we substitute this value. So let us see. So vc vector is 2 into 2 I cap minus 3 j cap plus 3 into 1.0 I cap plus 6.0 j cap upon 2 plus 3. And by solving, what we get, vc vector is 1.4 I cap plus 2.4 j cap meter per second. So this is velocity of mass center. Now we calculate velocity of both the vehicles with respect to mass center or velocity of both the vehicles in center mass frame. So find velocities of the particles in the center of mass reference frame. So here in center mass frame, what we do, we simply subtract velocity of the particle and velocity of mass center. So velocity of the first particle in center of mass frame, what will be? We subtract this velocity from this velocity. So v1 with respect to c is what? v1 vector minus vc vector. v1 vector minus vc vector. Let us substitute value. So 2 I cap minus 3 j cap is v1 minus 1.4 I cap plus 2.4 j cap. And by solving this, what we get? 0.6 I cap minus 5.4 j cap. So that is velocity of the first particle in the center mass frame. Similarly, we can calculate velocity of the second particle with respect to mass center. It means velocity of second particle in center mass frame. So what we get? We subtract velocity of mass center from v2. So v2 with respect to c is v2 vector minus vc vector. Here it should be v2 vector. So we substitute value of v2. So what? 1 I cap plus 6 j cap minus 1.4 I cap plus 2.4 j cap. And by solving, what you get? Minus 0.4 I cap plus 3.6 j cap meter per second. That is velocity of second particle with respect to mass center. Now we verify the idea. The total momentum of the system must be a null vector in center mass frame. So in the C part, find total momentum of the system in the center mass frame. So what we do? We simply add m1 v1 with respect to c plus m2 v2 with respect to c. So what you do? Mi vi with respect to summation. So it will be m1 v1 with respect to c plus m2 v2 with respect to c. For m1 we substitute 2 kg. For this we substitute this velocity. So what we get here? 2 into that is here this 0.6 I cap minus 5.4 j cap, and for second 3 into this velocity minus 0.4 I cap plus 3.6 j cap, and by solving this you will get 0. I am leaving the calculation verification on you. So these are very simple problems in which what we have done, we have simply calculated velocity of mass center and velocity of particles or different bodies with respect to mass center, and verified that total momentum of a system in center mass frame will always be a null vector. Now we proceed how to apply Newton's laws in center mass frame. Actually, we know that what we know after studying that with the knowledge of action forces, we will become capable of predicting motion of center mass frame, and that is biggest advantage. So let us proceed for that. Newton's second law on a system in the center mass frame. We proceed developing Newton's second law in center mass frame from the idea what we have developed in Newton's law, that Newton's second law for a system of particle in inertial frame. What was that? Net actional force is equal to total effective force on the system. Here we have seen that the total sum of all the internal forces is becoming a null vector. So we proceed with the same idea here. Newton's second law for a system of particles in an inertial frame, what is that? Summation Fi vector is equal to summation Mi Ai vector. What is this? Fi is external force on the ith particle. So this is what? Net actional force on the entire system. And this is what? Net effective force on the entire system, we call this equation to be 1, and we know that this equation is perfectly true. Now we know that if center mass will be accelerated, frame of center mass will be a non-inertial frame. If center mass is not accelerated, its frame will be an inertial frame. So what it will be? Depending on the net axial force is a null vector or not, the center of mass frame is an inertial or non-inertial frame. So let us discuss again. And before discussing both the cases simultaneously, let us take general case that center mass is accelerated, so its frame is an non-inertial frame. And let us assume acceleration of center mass to be AC vector. So we have to add, in addition to all the real forces, the pseudo force also. So for M1 particle, what will be pseudo force? Minus M1 AC. For M2, what will be pseudo force? Minus M2 AC. So in this way, we will add all the pseudo forces with this real force, and what you get on the side? Total mass into acceleration vector with respect to mass center. But before going to that, what we do? Simple thing. What? We know that this equation is correct. So we add both the sides a quantity what? Summation of all the pseudo forces on that side and also on that side. As a general case, let us assume the mass center to have acceleration AC vector. Thus, in the center of mass frame, on a particle of mass mi, a pseudo force minus mi AC vector has to be assumed acting in addition to the external force. The equation representing the Newton's second law can be written as, now I am not writing equation in center mass frame. What we are doing, we summation of this such kind of term for the entire system, we add on this side and on that side also. So equation will remain balanced. So summation fi vector plus summation minus mi AC vector is equal to summation mi ai vector plus summation minus mi AC vector. Now what is that? This is total external force on the system, that is net pseudo force on the system in the center mass frame. Now let us interpret what is this. Let us divide this into its constituent term. What? M1 A1 vector plus M2 A2 vector and so on. Similarly, minus M1 AC vector minus M2 AC vector and so on. Now M1 M1 term group, M2 M2 term group. So what you get? M1 A1 vector minus M1 AC vector. Take M1 common. So what you get? M1 A1 vector minus AC vector, and A1 vector minus AC vector is what? A1 with respect to C. What we get here? M1 A1 with respect to C plus M2 A2 with respect to C and so on. So what we get ultimately here? Summation Mi AI with respect to C. So let us proceed further. So it is summation Fi plus summation minus MIAC is equal to summation Mi AI minus AC, what we had taken, grouping the terms. And what is this? AI with respect to C. So summation Mi AI with respect to C. And now we know that this quantity is null vector. We have seen from the fundamental properties of center mass frame. So putting it null vector, what you get? Since total effective force in center mass frame is a null vector, summation Mi AI with respect to C is a null vector, we can write summation Fi plus summation minus MIAC is equal to null vector. Now we bring this on that side. So what you get? Summation Fi is equal to summation MIAC. Now we can take AC out of the summation sign. So what we here? Summation Mi into AC. And this quantity in parenthesis, what it represent? Total mass of system. And we denote it by capital M. What we usually do. So what you can write here? Capital M into AC. So what you get? Summation Fi is equal to M into AC. Equation number 2. This is very important equation. What it suggests? That from the knowledge of external forces on system, we can predict acceleration of mass center. And if you know the initial condition, means initial position and initial velocity, we can predict the motion of the mass center. So knowledge of external forces will help us to predict motion of mass center and in turns motion of the center mass frame. Now if it is simpler to analyze problem in center mass frame, and we know the motion of center mass frame from the knowledge of external forces, we can find the net result from in laboratory frame, or you can say in ground frame. Let us how we can utilize this idea. Let's discuss with the help of an example. Example 3. Two blocks A and B of masses M1 and M2 connected by a spring of a relaxed length L0 are placed on a frictionless horizontal floor. A constant force F is applied on one of the blocks as shown in the figure. You can see here. So the force is applied on the block B. Block has mass M1, block B has mass M2. The relaxed length of the spring is L0. Now what is asked? Find the displacement of the blocks when the extension in the spring becomes excess at the time tau. Let us here, when the extension becomes excess, time is tau. What you do? Suppose you try to analyze this problem in ground frame. We know the time, tau. It is given. Of course, it is not written here. So, but assume time tau when the extension becomes excess is given. But to calculate acceleration of both the blocks is not a simple task, because how the spring force is varying we don't know. And the spring force is necessary to find acceleration of both the blocks. So in the ground frame, this problem becomes somewhat difficult to calculate. But in center mass frame, it will be very simple. Let us see. Configuration of the system and various quantities of interest at the instant t is equal to 0 and t is equal to tau are shown by their usual symbols in the following figure. Say here, at the beginning when t is equal to 0, force is applied and this system will begin to move here and the spring will get extended, and now at time tau, support extension has become excess and this way. And we can locate here this from this point to that point. This is displacement of particle A, x1. We have to find this one, displacement of blocks. And similarly from here to here, this will be displacement of block B, x2. So we have to find x1 and x2. Now let us see, to use center mass frame, we have to locate where center mass frame, and with center mass of the two particle system, that we know that center mass of a two particle system divides the separation between them into reciprocal or inverse ratio of their masses. So what we can write, suppose here is C. So with C, we can attach a reference frame. So it is center mass reference frame. Now distance of A1, we denote it by x0 1 with respect to C. Why not at t is equal to 0? For B, we call x0 2 with respect to C. Now similarly here center mass here. Now we can see center mass frame. So this will be x1 with respect to C at time tau. This will be x2 with respect to C. Of course, we know that these two distances, what? They will divide this separation in the reciprocal ratio of masses. So if this L0, what will be? M2 L0 upon M1 plus M2, what it will be? M1 L0 upon M1 plus M2. Similarly for that, this separation is what? L0 plus xs, what you can write here? This is M2 L0 plus xs upon M1 plus M2. What it will be? M1 L0 plus xs upon M1 plus M2. But let us proceed how we can arrive on that result. This is displacement of mass center xc. And that we can predict very easily. What? We know that acceleration of mass center is what? This force upon total mass M1 plus M2. And half into this acceleration into tau square is displacement xc. That we know. Only thing is what? We have to calculate displacement of the masses with respect to mass center. So for that, what we do? For the instant t equal to 0 and t equal to tau, what we can write? At 0, x0 1 with respect to C plus x0 2 with respect to C is equal to L0. That is the relaxed length. Similarly, x1 with respect to C plus x2 with respect to C is equal to L0 plus xs. Equation number 2. Now by subtracting the left hand members from left hand members and right hand member from right hand member, what we get? Subtracting the left hand members from the left hand members and the right hand members from the right hand members of the equation of these two equations, what we get? x1 with respect to C minus x0 1 with respect to C. Similarly, x2 with respect to c minus x naught with respect to c, and on the right hand side we get only x's. The expressions in first and the second parenthesis of the above equation are the displacement of the first and the second block with respect to the mass center. Why that displacement? Let us see. Denoting them by delta x1c and delta x2c, what we can write? Actually, this is a change in position of block A with respect to mass center. That is, change in position of block B with respect to mass center. So they are displacements in the center mass frame. We denoted them by delta x1 with respect to c and delta x2 with respect to c. What we can write? Delta x1 with respect to c plus delta x2 with respect to c is equal to xs. Let us call equation number 3. Now let us proceed further. Knowing the fact that the mass center of a two-particle system lies on the line joining the two particles and divides the distance between them in the inverse ratio of their masses, we can write that x01 upon x02 will be equal to x1 with respect to c upon x2 with respect to c, and they will be equal to reciprocal ratio of masses. Let us see here. x0 1 with respect to c upon x2 2 with respect to c, x0 2 with respect to c will be x1 with respect to c upon x2 with respect to c is equal to m2 by m1, because for a two-particle system, center mass will always divide the separation between their reciprocal of masses. Now, what we do further? Substitute this term from that term and this term from that term. Again, we take the same ratio. With the from ratio property, you will see that difference of that and difference of that, the ratio will be same. So, what you can write? From the above equation, we can write x1 with respect to c minus x0 1 with respect to c upon x2 with respect to c minus x0 2 with respect to c is equal to m2 minus m1, and this will be delta x1 with respect to c. This is what delta x2 with respect to c. So see here, the numerator and denominator of the left hand side of the above equation are displacements of the block relative to the mass centers in the time interval t equal to 0 to t equal to tau, denoting the displacement by delta x1 with respect to c and delta x2 with respect to c. As we had done earlier, what we can write? Delta x1 with respect to c upon delta x2 with respect to c is equal to m2 by m1. So delta x1 with respect to c upon delta x2 with respect to c is equal to m2 by m1, equation number 4. Now, what equation number 3 suggests sum of these two quantities. So by using ratio and proportion, we can find these values. So what we do? From the equation 3, what is that? Delta x1 with respect to c plus delta x2 with respect to c is equal to xs. And equation 4, what we can write? It is very simple. Delta x1 with respect to c will be m2 xs upon m1 plus m2. And delta x2 with respect to c will be m1 xs upon m1 plus m2. No need to explain how we can arrive on that. So let us call equation number 5 to these two combined result. Now what we do? We have obtained displacements of the blocks with respect to mass center. Only we have to find displacement of the mass center in the given time interval. For that, we apply the Newton's law on the entire system. Applying Newton's second law on the system, what we get? Summation Fi external is equal to total mass into AC. So with this way, we can find AC is F upon M1 plus M2. No need to put vector sign because we know it will be towards right, because force was only force, it was towards right. Now we, in time 2, what will be displacement? We know that the center mass begins from rest. So using the second equation of uniform acceleration motion, what you get? Xc is equal to half into AC into tau square, because initial velocity was 0. So the acceleration of the mass center remains constant and it starts from the rest. Thus, the displacement Xc of the mass center is given by Xc is equal to half AC tau square. So substitute the value of AC. So what you get? XC is equal to F tau square by twice M1 plus M2. So we know equation number 6. Now what we know? Say the result written in equation 5 and equation 6. These quantities we have shown in the diagram. Now we again redraw the diagram and show these quantities. See here. Configuration of the system at the instant t equal to 0 and t equal to tau, and equation 5 and 6 are reproduced here for the reference. We are rewriting here. So that was the diagram. You can visualize. So equation of this x1 with respect to c, m2 xs upon m1 plus m2, and x delta x2 with respect to c is m1 xs upon m1 plus m2. This was combined to result, we have said, equation 5. And what is equation 6? xc was f tau square upon twice m1 plus m2. Now we can see from this situation, what is x1? x1 is, you can see, just see, from displacement of the block A. Now realize from here, x1 is equal to xc plus x naught 1 with respect to c minus x1 with respect to c. What? This is xc. So add this and subtract this, you will get what? X1. Just see, we start from here. So if you add this one and subtract this, you will get x1. So it is not difficult to understand. Now we substitute the values. So this is what? Delta x1 with respect to c. Group it. So this is just bring it minus here. So it will minus sign, order is replaced. So it is what? Delta x1 with respect to c. So x1 is what? xc minus delta x1 with respect to c. Substituting from equation 5 and 6 into the above equation yields the displacement of the block A. What it will be? xc f tau square upon twice m1 plus m2 minus this quantity m2 xs upon m1 plus m2. By the similar analysis, what we get? A similar analysis yields the displacement of the block B. What is that? x2 is equal to f tau square upon twice m1 plus m2 plus this. Now if you do this kind of thing, what you get? x2 is equal to xc plus this term. It is not difficult. So I am leaving it to verify this result on you. So in this way, what we have done this one, actually calculating displacement of the blocks with the knowledge of Newton's law in inertial frame. The spring force was unknown, so we cannot account for it. Then what we have done? Actually, why it is unknown? I am saying the spring force is known as a function of extension spring, and how extension spring is varying with time is not known. So spring force as a function of time is unknown. So in the ground frame, this is very difficult. But in center mass frame, what we can say? We can calculate easily displacement of the blocks with respect to center mass. And with the knowledge of Newton's law, we can predict motion of center mass or motion of center mass frame. So by relative motion compensation, we can calculate it, or we have calculated displacement of the blocks. So that is an idea how we can use Newton's law in center mass frame. Now we come on momentum methods and the center mass frame. In center mass frame, we know that total momentum of a system is always a null vector. So momentum in center mass frame is always conserved. So it may give advantage to some times, but we'll discuss some other aspects here. Actually, the first idea what I told you here, total linear momentum of a system in center mass frame is a null vector. So summation mi vi with respect to c is a null vector. So in center mass frame, the total linear momentum is always conserved and its value is always a null vector. But what we can predict from here, one other things. Total mass moments in center mass frame is a null vector. What? Summation mi ri with respect to c is a null vector. Now taking differential, what we take? Summation mi delta ri with respect to c is what? A null vector. Again, we can arrive on that equation by integrating this equation or on that equation. So what you can see, total sum of product of masses into displacements of each particle in a center mass frame is a null vector. So this idea can be used to relate displacements of various particles in center mass frame. Other than this, what you can see, in any reference frame, total momentum of a system is equal to the momentum of the mass center. Means in any other reference frame, total momentum of system is equal to momentum of the mass center. Means multiply velocity of mass center into total mass, you will get total momentum of the system. So writing total momentum in any reference frame is very simple if you're using concept of center mass. What is that? Summation mi vi is total momentum in any frame is equal to mvc. So this is again a simplification. So summation mi delta ri is equal to summation delta rc. What is get? Here again we can relate displacements of various particles with the displacement of center mass in any other frame. Again, here the same idea I have communicated with respect to center mass, here with respect to any other reference frame. Now we discuss conservation of momentum in any other frame. Means of course in center mass frame it is always conserved, there is it is a null vector, so it does not need any further discussion. We discussed our earlier conservation momentum in inertial frame. So what is that? In absence of external forces on the net external force, total momentum of a system remains conserved. So what we can write here, if summation fi is equal to 0, summation mi vi is equal to mvc is a constant. So that is the principle of conservation of momentum what we studied earlier. But if summation fi is 0 and vc is also 0, so what we can write? Summation mi ri vector is equal to a null vector. Again, if vc is 0, displacement of center mass will be 0. So that was the area what I have discussed in the introductory screen, the Mann-Planck system. Of course, these ideas are not very difficult and I'll require you to revise them and understand. But let us see how can we use these ideas in analyzing physical situation or real problems. So let us take example 4. A man of mass small m is standing at one end of a plank of mass capital M and length capital L. The plank is at rest on a frictionless horizontal floor. The man walks to the other end of the plank. Find displacement of the plank and man related to the ground. The situation is given and the same situation what we have discussed on the introductory screen. Here we have given coordinate system. Horizontal direction is x and vertical is y. The man is standing here. There is no friction between the plank and man. What the man does? The man walks on the plank to the other end. During this time, what will be displacement of the plank and that of man with respect to ground? Because plank is also moving. So displacement of the man is not simply minus L on this side with respect to ground. It will be smaller than that. And what will be displacement of plank? So how we can relate this? Here the idea what we discussed earlier will be very useful. Just see, before the man started walking, the system was at rest. And in the horizontal direction, there is no external force. So in the horizontal direction, there will be no acceleration of mass center. And initial velocity of mass center will be was 0. So mass center will be at rest. So displacement of mass center will be 0. So what we can write? Summation mi delta ri is equal to a null vector. So this idea we use here. Now there are no external forces on the Mann-Planck system in the horizontal direction. Therefore, we can write the following general relation. What? Summation fx equal to 0 and vc is 0. Therefore, what we can write here? Summation mi delta xi is equal to 0. If vc were not 0, so what we written here? Some total mass into delta xc. There may be such kind of situation in some problem. We'll see later on. So here, now we put the values. Here, what is delta xi? Displacement of the man with respect to ground. And what is, again, displacement of plank with respect to ground. So we denote plank by small p and man by small m, or 1 or 2 subscript. Denoting the x coordinate of the man, mass center of the plank, and mass center of the man plank system by xm, xp and xc. We can write the following equation. Actually, we can locate the mass center plank here. So displacement of the plank will be equal to displacement of mass center plank. So we denote it by xp. So what you can write here? Summation mi delta xi equal to 0. What it shows? So mx delta xm plus capital M delta xp equal to 0. Here m is mass of the man and delta xm is displacement of the man. Capital M mass of the plank and delta xp is displacement of mass center of the plank, means displacement of the plank. Their sum must be 0 according to this equation. Now we have to substitute values only, but none of these values is given directly. What we know? Displacement of the man with respect to plank is L towards the left. So here, again we have to write relative motion idea. So displacement of man related to plank. What delta xm with respect to plank is minus L. So we know this direction to be what? Negative, and this is positive x. So ideas of relative motion suggest that delta xm is equal to delta xp plus delta xm with respect to p. Again, we are using one dimension. So we use this direction to be positive, this direction to negative. Delta xm we have to find here and substitute here. But delta xp is again unknown. But delta xm with respect to p is minus L. So let us substitute value. So delta xm is equal to delta xp minus L. Now we have two equations and two unknown. Delta xm and delta xp, and these two independent equations. Now we can find solution. So what you do? We substitute delta xm here, so we'll get delta xp. Again, if you substitute delta xp, you will get delta xm. So let us see. From the equation 1 and 2, we get. So solution of equation 1 and 2 is not very difficult and you can solve it. So the answer will be m delta xm plus m delta xp will be 0, this equation, and we substitute here m into delta xp minus L plus m delta xp equal to 0. From where what you can write? Delta xp is equal to m small m into L upon m plus m. Now substituting this delta xp in this equation, we will find delta xm. And now we come on the next example, example 5. Actually, previous example was not very difficult. It was a very common example you will find any other textbook. So please try to understand that example carefully. Now let us see what is the next example. In a free space, two particles of masses 2 kg and 3 kg were observed at an instant at point -2, 1, 4 and 2, -3, 6, moving under their mutual interactions with the velocities 3 I cap minus 2 j cap plus k cap meter per second and minus I cap plus j cap minus 2 k cap meter per second. If after 10 seconds the first particle passes the point this, find the coordinate of the point where the second particle passes at this instant. Actually, these two particles, their initial positions are given, their initial velocities are given, and it is known that after that instant there are no external force on the system. Before that or till that instant when the particles are here, there may be external forces on the system, but after that instant they are moving under their mutual interaction, so there is no external forces. Now what did you find? Find coordinates of point where the second particle passes at this instant. When the first particle here, where will the second particle? So how will proceed? Here we have to use vector notations. So displacement of particles and mass centers of the system bear the following relation. What? Summation mi delta Ri vector is equal to total mass into delta Rc vector. Because here we can see the mass center is not necessary. You can find these velocities are given. So by using 2 into this velocity plus 3 into this velocity upon total mass, this will give you velocity of mass center. So mass center is moving here. In the previous problem, of course, I have taken very simple problem. It was one dimensional and stationary mass center. But in second problem, what I am doing? A three-dimensional problem with the moving mass center. So in previous case, this sum was a null vector, but here we'll get this one. So we have to substitute values according to this equation. So what you get? M1 delta R1 vector plus M2 delta R2 vector is equal to capital M into delta RC vector. One will be the particle of mass 2 kg and substitute 2 stands for particle of mass 3 kg and capital M is 2 plus 3. So denoting the unknown position coordinate of the 3 kg particle by XYZ, we can write. So here this way, let us see what we have written. So what is this? For 2 means first particle. Here both the coordinates are given. So what is delta R1? Final coordinate minus initial coordinate. So 2 into final, 6 minus 2 plus into I cap plus 8 minus 1 j cap plus minus 6 minus 4 k cap. So that is what? M1 delta R1. Now what we can write for M2? 2 into its displacement. Its final position coordinate we assume XYZ. So what will be? X minus 2 I cap plus Y minus 3 j cap plus Z minus 6 k cap. So that is M1 delta R1. This is M2 delta R2. What is this will be equal to capital M into delta RC. So capital M into delta RC. We'll substitute its value later. Now let us simplify it somewhat. So it will be 16 I cap plus 14 j cap minus 20 k cap. Not very difficult. You can verify how much it is. This 6 minus 2, 8 into 2, 16. So we can verify the terms. Now we'll leave it as it is. 3 into x minus 2 I cap plus y minus 3 j cap plus z minus 6 k cap. So this will be m into delta RC. So we have simplified this term here and we have kept other things intact. Let's call equation number 1. There are no external forces, thus mass center moves with a constant velocity. So velocity of mass center will become constant. Displacement delta RC of the mass center will be velocity of mass center into the what is time requirement. So delta RC will be what? Vc into delta t. And after 10 seconds, time is given. So how we can calculate velocity? 2 into this velocity plus 3 into this velocity upon 2 plus 3. So delta RC will be what? M1 V1 vector plus M2 V2 vector upon M1 plus M2. M1 is 2, V1 this velocity, M2 is 3, V2 is this velocity, and delta t is 10 seconds. Let us substitute values. 2 into 3 I cap minus 2 j cap plus k cap plus 3 into I cap plus j cap minus 2 k cap upon 2 plus 3 into 10. Now we'll solve it. What you get? Delta RC is equal to 6 I cap minus 2 j cap minus 8 k cap. So we have obtained delta RC. That is equation number 2. Now we proceed further. Substituting delta RC is equal to what? 6 I cap minus 2 j cap minus 8 k cap from equation 2 and m is equal to 5 into equation 1. So what we get? This first term, it was 16 I cap plus 14 j cap minus 20 k cap, and second term just we are keeping intact. So what we get here? That's mass 5 into this. 5 into 6 I cap minus 2 j cap minus 8 k cap. Now by solving this equation, we can find x, y and z, all the coordinates. So what do we get here? 16 I cap plus 14 j cap minus 20 k cap. This is 3x I cap minus 6. And it is what? 3y plus 9 j cap. This 3z minus 18 k cap. This. Now what we do? Equating coefficients of I cap, we get. If you equate both the sides, coefficients I cap, what you get? X coordinate. So it will be 16 plus 3x minus 6 is equal to 30. And by solving this, what you get? X is equal to 20 by 3 meters. Similarly, equating the j coefficients, j cap coefficients, what you get? Y coordinate. So what it will be? 14 plus 3y plus 9 is equal to minus 10. 14 plus 3y plus 9 is equal to minus 10. And by solving, what you get? Minus 11. So y coordinate of the second particle is minus 11 meter. And similarly, by equating coefficient of k cap, what you get? Z coordinate of 3 kg particle. So if you get Z coordinate, what you get? Minus 20 plus 3z minus 18 is equal to minus 40. So equating coefficient of k cap, what we get? Minus 20 plus 3z minus 18 is equal to minus 40. And by this, what you get? Minus 2 by 3. So we have obtained the coordinates of the second particle. So in this way, we can have two kinds of situation. Mostly in the textbook, the problems what you find in which center mass will remain at rest, but center mass may be moving. So if center mass is moving, we have to compensate for that velocity. So required coordinates of the 3 kg particle are what? 20 by 3, minus 11 and minus 2 by 3. So these are the two prototype problems. Now let us proceed further on the next example, example 6. What is that? Let us see. A sleeve of mass m can slide on a frictionless horizontal rod fixed between two rigid supports. A small ball of mass m is connected with the sleeve with the help of a light inextensible thread of length L. The ball is held maintaining thread horizontal and straight as shown in the figure and then released. Find displacement of the sleeve when the thread has turned through angle theta. Now this situation we have taken in previous lecture. At that time, we have calculated displacement of sleeve with the help of some elaborate method. And at that time I have said that this displacement we can find with the help of center mass much easily. Now we will see how we can find displacement of the sleeve. Again, what we use here on the system, there is no external force in the horizontal direction. So there will be no acceleration of center mass in the horizontal direction. First thing. And initially the setup was at rest. So center mass initial velocity is 0. So center mass x velocity will be 0 because there is no acceleration in horizontal direction. Of course, in y direction, center mass will move. So there will be velocity of center mass in y direction. But we are interested in the displacement of sleeve that is only in x direction. So we have to concentrate only x displacement. Consider the system configurations at the initial and the final instance. So initially we draw the system like that. It is at t is equal to 0. And the system given as it is. Now at the final instant t equal to tau, we show the system thread has turned through an angle theta, and now we can show the displacement of the ball, horizontal displacement and displacement of the sleeve. Before that, we can show the separation between them became L cos theta. It is not very difficult to calculate because it is L. So this is will be L cos theta. Now from this point to that, this is displacement of the ball, horizontal displacement, delta xv. Now from this to that, this will be displacement of sleeve. So this is what? From this null position to this null position, you can see that is delta axis. This is displacement of the sleeve. Now we have to calculate this. Now we can use the same idea that center mass was at rest, so it will remain at rest. So summation mix delta xi will be a null vector. So we assume here xy. The geometry suggests, what geometry suggests? That delta xs plus delta xb is equal to L1 minus cos theta. Why? Because this separation is L, this separation is L cos theta. So sum of this plus this is what? L minus L cos theta. So L we can take common. So delta xs plus delta xb is equal to L1 minus cos theta. Again, that is equation number 1. Now, in absence of horizontal external forces, movements occur in the system from rest. Thus, there is no displacement of center mass. So what we can write here? Summation fx is equal to 0 and vc is equal to 0. So what we can write? Summation mi delta xi will be 0. Here we are using one dimension, so there is no need to use vector sign. So what we can write from denoting the x coordinate of the ball by and the sleeve by xb and axis. We can write m into delta xb minus m into delta xs equal to 0. Here I am putting minus sign because we know that here this is in this direction. So this direction will take positive, this is negative. Now we have to calculate delta xs. Call this equation 1. So this equation and this equation, we are having two unknown and two independent equations. There is no difficulty in solving that. From equation 1 and 2, we get delta x is equal to m upon m plus capital M L1 minus cos theta. Now we can calculate. It is not very difficult to calculate. So in the previous lecture, I have told you that this displacement problem we can simplify with the help of concept of mass center. At that time, we have used with the help of Newton's law and momentum methods. Now let us come on the next example. Example 7. A shell fired from the ground with a velocity u to hit a target on the ground at a distance r from the point of firing. But the shell explodes in two identical fragments at the highest point of its trajectory. If one of the fragment falls vertically downwards, where will the other fragment hit the ground? Actually, this problem we have taken in the previous lecture also. At that time, we have done it with the help of conservation of momentum and kinematics. Now, the same idea we can solve with much simplicity with the help of idea of center mass reference frame. How we proceed here? Let's see. First idea, very important. The explosion occurs at the highest point, where vertical components of velocities of both the fragments remain zero after the explosion. Therefore, both the fragments after the explosion will take half of the air time and hit the ground simultaneously. Actually, explosion occurs at the highest point. At the highest point, there was no vertical component of velocity in the shell. Again, at the highest point when explosion occurs, momentum is conserved. So, one of the fragment has acquired zero velocity because it falls vertically downward. So, other fragment will also have zero velocity in vertical direction. So, both the fragment have no velocity in the vertical direction. So, they begin falling from zero vertical velocity. So, both will take equal time to hit the ground, and that time will be half of the time of flight. That is what after the maximum time, maximum height. Another idea that is again very important. Since both the fragments remain in there for the same time interval, net external force remain unchanged. Therefore, after the explosion, the mass center of the shell will follow the same trajectory that the shell would have followed if explosion were not occurred. Let us see here. Actually, after the explosion, both the fragment will hit the ground simultaneously. So, on the entire system during the flight, the only external force was gravity. So, here we know that acceleration of mass center is equal to net external force upon total mass. So, acceleration of mass center will not alter. So, mass center will move in the same way as it was earlier. Again, please take care of mind. If one of the piece has acquired a vertical velocity, so it would hit the ground at some other time. Suppose a fragment which acquires a downward vertical velocity, it will hit the ground earlier than the other fragment. In that case, till the first fragment hits the ground, till that moment, center mass will follow the same trajectory. Because till that moment, again net external force is weight. Because when the first fragment hit the ground, an external force from the ground starts acting. So at that time, trajectory of center mass will change. We'll discuss this in some later in advanced example. But again here, both the fragment hit this ground simultaneously. So there is no additional external force. So what we can say, center mass will follow the same trajectory as it had followed if explosion were not occurred. In the figure, locations of both the fragments and the mass center are shown when both the fragment hit the ground see that idea. At this point, explosion occurs. So here the first fragment will follow this path. Second fragment will follow this path. Let us, so we don't know what is the path is. But center mass will follow the same path as the unexploded shell would have followed. So here is mass center. So at this time, we again locate, just see here, the relate the position of this fragment, and position of mass center. Now let us see how we'll proceed. This we know that is 0.5 r. The location of mass center is, we know this r, and that say it is unknown x. So we can here use the concept of definition of mass center. What? m1 x1 plus m2 x2 is equal to total mass into x. So what we do here, summation mi ri vector is equal to mass into rc. So that is what in vector form, but in scalar form what will be m into r by 2. This mass is small m. We have using total mass of shell to be 2m. Just see here. So for first particle m into r by 2. For second particle m into x, that is unknown. For the mass center, total mass 2m into r, because it is at distance r. And by solving this, you get x is equal to 3r by 2. So if x is 3r by 2, means this second fragment will hit what? 0.5 r ahead of the target, because target was here. The second fragment hits the ground at a distance 0.5 r ahead of the target. So today we have taken 3 problems and seen how the use of center mass and its reference frame can simplify several problems. Particularly we have taken today use of Newton's law and momentum method. In the next part lecture of this part B of this lecture, we will discuss energy methods, and discussion of energies method is going to be more interesting, because in energy method the momentum conservation and Newton's law all will be involved. So before we proceed with the we assemble for the next lecture, I will suggest you to revise this lecture thoroughly. Thanks for patient listening. We'll meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.